Welcome to the full work solution from the FEEG1003 Thermofluids workbook. And we're going to solve, today I'm going to be solving question 4.5, which is in the dimensional analysis chapter. Okay, the usual caveat applies with these solutions. Don't watch the video in full without having attempted the question. And at any point when watching the video you think you've unlocked enough stuff to give you a good idea of how to finish your attempt, you can always pause the video, carry on, see how far you get, unpause the video, etc. Okay, so make sure you don't waste any of these full solution videos by watching them before you've had an attempt. Okay, here's the question. We've got an aircraft example here. So we've got a thrust of a family of propellers, and then we're given a list of variables that are part of this problem. So the angular velocity, the forward velocity of the aircraft, the diameter of the propeller, the viscosity, the density, and finally the speed of sound. And this question is in two parts. So the first part is to find an expression for the non-dimensional thrust. So it's clear we're going to have to do some Buckingham pi or Rayleigh analysis, in this case Buckingham pi, to find a dimensionless group that contains the thrust term. And then the second part says that full similarity is not possible, assuming blah blah blah. Find the thrust of a propeller of diameter, etc., etc., given that the model has the following properties. So that's the part where we've already done the Buckingham pi in part A, and part B is where we're going to find the use this dimensionless group that we've calculated, and then just like Reynolds number, Froude number, other dimensionless groups, we try and keep similarity between those two properties. So if we're doing some fluid experiments and Reynolds number was our key dimensionless group, we try and keep the Reynolds number the same in the large thing and the small thing. So the same in the prototype, the full-scale machine, and then the model as well. And that gives us similar flow conditions. So Reynolds and Froude would give us similar flow conditions. So we're going to find a dimensionless group with thrust in it, and then using the parameters that were given in part B, work out the scaling law. So work out the different dimensions and thrusts and RPMs, in this case, of the big propeller and the small propeller. Now this is going to be one of two videos on this question because I'm going to do it two different ways. Okay, I'm going to choose two different sets of fixed and repeating variables because both give you subtly different answers, and the way this question is set is quite a clever question in a way. So I'm going to show you two ways which are equally valid, equally as lengthy, but solve the problem in slightly different ways. Okay, so as we always do, we need to highlight the bits of the question quickly that we're interested in. So we need to find this non-dimensional thrust in terms of non-dimensional parameters. So we need to do Buckingham pi theory. Okay. And then this bit is quite interesting here. Assuming that the Reynolds and Mach numbers are the least significant parameters. So it's already given us a bit of a clue or a hint that we should expect Reynolds number and Mach number to come out as dimensionless groups. Okay, we both know, or we know that both of these are dimensionless groups. The Reynolds number is the ratio of inertial to viscous forces, and then the Mach number is the local or the body speed divided by the speed of sound. So then it says find the thrust of the propeller, and then we're given the full scale diameter, the rate of rotation in RPM, so we need to convert that. And then we've got a model propeller with 1 meter. There's the thrust, and there's the rotational rate. Okay, so we're asking to find the thrust of a full-scale propeller of that diameter rotating at 6,000 revolutions per minute. Okay, so that's the second part of the question where we actually take that dimensionless group and do something with it. Okay, so over to the board now. I'm going to show you two different ways, and I'll split this video up into two parts. Okay.
Right. So onto the board. The next thing we do with any engineering problem is is to draw a diagram. That's not really relevant or very useful in dimensional analysis problems. So I've done the next best thing, or the more relevant thing, which is to list out all of the 7 variables in the problem, and then also list their fundamental dimensions. So we've got the force on the propeller, mass length times the -2, always a good one to remember. Velocity, dynamic viscosity, the diameter, so its length, the rate of rotation, the density, and speed of sound. That's all 7. There's 3 fundamental dimensions in this problem, mass, length, and time. So 7 minus 3 equals 4 dimensionless groups. So that means of these 7, 4 of them are going to appear once in each of the 4 groups, and 3 of them are going to appear, at least initially, in all of the groups. So now we need to choose the repeating and the fixed variables. So to choose the repeating variables, we use the rules of the game that we understand, which is that we have to include all dimensions in the problem, have to appear in the repeating variables. So we need mass, length, and time somewhere. The combination of those variables cannot form their own dimensionless group, because when you do the dimensional analysis, and bucking and pi in this instance, if they're dimensionless, then you will actually end up with a dimensioned group, so it won't work. And finally, they need to be easily measurable in practice. Okay, this is a way really of prompting you to choose the most simple parameters. So we've got mass, length, and time to consider. We'll start with the mass one. We've got force, dynamic viscosity, and density. We're going to choose density in this case, and generally, as a rule, if you have a bunch of variables like this and you need to include mass in your repeating variables, choose density if it's there. The only other more simple one is mass itself. So we're going to choose that one. And it's a lot easier to measure density than certainly dynamic viscosity, because it's very difficult, and force as well is a little bit tricky. So that's the easiest one to measure. And then I'm going to choose 2 other parameters that have length and time in. Diameter, just because it's a tape measure job, dead easy. And then it's quite easy to measure the velocity of something. Okay, so they're going to be my 3 repeating variables, and they're going to appear at least at the beginning of every dimensionless group. And then force, dynamic viscosity, rate of rotation, and speed of sound are going to appear once in each of the pi groups. Right, so now off to do the bucking and pi, and I'll do it in full for the first group, and then I'll do it more briefly for the others. Right, so for our first pi group, we've got our 3 repeating variables, and then the first of our fixed variables, which is the force. And then we raise each of the repeating variables to a power. You can call them whatever you like. I've called them A1, B1, and C1. It really doesn't matter as long as you do it. And we don't raise the fixed variable to any power. Okay, that's just the rules of bucking and pi. Next, I'm going to put in the fundamental dimensions of each one and write this out very carefully, raising each of those 3 to their respective powers. Okay, go steady with that step, and also with the next one. Okay, so there's density, diameter, velocity, and the force. variables. Okay, the first three all raised to those powers. Now we're going to work out the value of these powers by equating each of the dimensions in turn. Okay, now length appears an awful lot, so we'll do that one last because we can't solve it straight away. It's always usually easier to start with mass and then time and then length. So if you do it for mass first, nice and steady with this step. So there's an M, A1, nothing, 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 1 there as well, plus 1. Okay, so A1 equals minus 1. Do the same for time. So minus C1, and then time to the minus 2 at the end here, minus 2. So therefore C1 equals minus 2. And then finally for length, this is why we don't do it first, generally. So minus 3A1 plus B1 plus C1 plus 1. I think that's right. Okay, work that through. B1 equals minus 2. You're going to have to substitute in A1 and C1 into this to solve it. Now we put these powers back into this. Okay. That's our first dimensionless group. What you can do now, if you don't believe in the magic, you can put mass length times the minus 2 up there, add in these dimensions, making sure to square those two, cancel it all out, and it should equal 0. Okay, so you can prove to yourself it is dimensionless. Okay, I need to rub off some of this stuff to make some space. Oh, shouldn't have rubbed off that second line, never mind. We'll do the same again now for the second pi group. So these will stay the same, and this time we add on dynamic viscosity. So we end up with that exactly the same expression, but the mass, length of minus 1, time to minus 1 at the end. Equate all three of the fundamental dimensions and solve for the powers again. That's your second pi group. Third pi group is going to have homing in here. This is an interesting one. This is what you might have spotted when I said that the repeating variables appear at the beginning of all three groups. Quite often we say they appear in all the groups, but in some cases, so in this case and the next case, some of them disappear. So you can see this has got dimensions at time to the minus 1. And there's a mass there, m. It's the only m. The 0 is going to have to equal a1 when we solve for mass. So actually, rho disappears from this next group. And you can quite quickly see how you can make a dimensionless group out of these three. Okay, so they start at the beginning, but sometimes they disappear. Okay, so that's the third pi group. Put them down. And then the fourth pi group, which has got the speed of sound here. We lose quite a lot of stuff from here. To make a dimensionless group, the speed of sound. Probably worked it out. we lose everything apart from velocity. So this is the ratio of velocity now. Okay, so that's our 4 pi groups. Now we read the second part of the question, part B. It explains that it gives us the variables for the full-scale propeller and all the variables for the small-scale propeller, so the mod one. What we have here is a dimensionless group that isn't quite in the right form because we've got a velocity in here. We've got no information about the forward speed of the propeller or any other speed of the propeller. However, all these groups are dimensionless, so we can combine them carefully whilst maintaining their dimensionless properties. Okay, the first thing we're going to do, in the question it said that the Mach number and the Reynolds number were least significant. And you can see we've almost got both those ones straight away. Pi 2 group is actually 1 over the Reynolds number. Okay? If you ask me what the Reynolds number of a turbulent flow is, and I say 1 over 10 million, you'll think I'm being awkward. Okay? So you'll ask me just tell me what the Reynolds number is. We can invert this very easily because the dimensions there equal the dimensions there. Okay? It's a ratio of inertial to viscous forces. So we can invert that to give us the Reynolds number. Similarly, we can invert this one to give us the Mach number, because the Mach number is the body velocity divided by the speed of sound. Okay, so that's 1 over the Mach number as it stands. We can just flip it over. Okay, we need to manipulate this group because we've got, in the question, we've got omega, so the rotational rate of the propeller. So we need to get rid of that d squared. Get rid of that v squared, because we have the diameter. The density is going to be the same in the model and the prototype. Now this group is very useful here, because we've got an omega and we've got velocity there. Okay, so if we invert that, so times this group by 1 over pi 3, and also square it, so we have a v squared on the top and a v squared on the bottom, they'll cancel out. So we do that, so looking at the board, just visualise that flipped over and everything squared. We end up with a modified pi 1 group of ft over rho omega squared d to the power of 4. And that's what we can use in the question. So the final part of the question is, we've been given the parameters from a full scale and a model. So we'll call the full scale one the prototype, P. And this is a dimensionless group. So this is characterizing the thrust on the propeller. So we want to use this dimensionless group, keep it the same in the big thing as it is in the small thing. Okay? In the same way that Reynolds and Froude number give us similarity of fluid conditions or flow conditions. This is why you have to do model tests and why we have supersonic wind tunnels to keep the Mach number the same, because the airflow around an object changes with the Mach number. So you need to be able to simulate the small thing at the same Mach number as the big thing. Okay, and then gives you similarity of conditions. So your model reacts in the same way as the large full-scale aircraft and vice versa. So all we write out is exactly the same equation. But this is for the model propeller. So this is the smaller one. Now we go back to the question. We can assume the density is 1.23 kilograms per meters cubed. It doesn't matter because it cancels out anyway. And then we've got the rotational rates of the small one and the big one, 5,000 and 6,000 RPM. Convert that into rotations per second. We've got the diameter of the large one, which is 2.25 meters. We've got the diameter of the small one, which is 1 meter. And we've got the thrust on the small one, which is 1.2 kilonewtons, I think. So we can rearrange that, plug in the numbers, cancel all out to work it out, or rearrange the formulas and solve the single unknown, which is the thrust on the large 2.25 meter diameter propeller. Okay, and that gives you the answer in the book. So that's how, at the end game part of this question, we solve for that. Okay, in the other video, part 2, I'm going to show you a different route through by choosing different repeating variables. Okay, and we could do this ad infinitum, we could do this endlessly, but I'll explain in the next one why there's two main routes to this question, and they're the two easiest ones. Okay, so the next route is going to use slightly different repeating of fixed variables to get through to here, with effectively the same amount of effort, but the effort's spread in different places. Okay, so finish this video and start watching the next one if you want to see the other way of doing it.